will be able to wire a universal motor speed controller circuit on the PCB and test it. Assemble the wired PCB along with the potentiometer and socket in a gang box and test. Test the speed controller with a lamp, fan and electric drilling machine. Check possible minimum and maximum speed adjustments using a contact-type tachometer. Let us collect the tools, materials and components required to do this practice. Trainees toolkit 1 set, electric hand drilling machine 1 number, contact-type tachometer with necessary attachments 1 number, wired lamp holder with lamp of 40 watts 1 number, main operated table fan of any make 1 number, resistors R1 10 kilo ohms 5 watts 1 number, resistor R2 470 ohms plus or minus 5% 1/4 watt 1 number, resistor R3 and R4 1 kilo ohms plus or minus 5% 1/4 watt 2 numbers, potentiometer RV1 1 kilo 1 watts 1 number, capacitors C1 2U2 63 volts 1 number, capacitor C2 100 nanofarad polyester 1 number, SCR C1060 or equivalent or any SCR of 400 volts and current rating greater than 3 amperes 1 number, transistor Q1 DT135 or equivalent 1 number, transistor Q2 DD136 or equivalent 1 number, diode D1 D2 1N4004 2 numbers, PCB board 3mm into 20mm 1 number, 100 into 75mm gang switch and socket used for conduit wiring to mount switch, socket and potentiometer 1 number. Let us discuss how SCR is used to control the speed of a motor. An SCR conducts when a gate pulse is applied to it, just like a diode. It has 4 layers of semiconductors that form 2 structures, namely NPNP or PNPN. In addition, it has 3 junctions labeled J1, J2 and J3 and 3 terminals, anode, cathode and a gate. One of the main applications of SCR is to control the speed of a motor by varying the input voltage to the motor. SCR is like a diode, but with added ability to be able to turn it on and off so that the electricity not only flows in one direction but only flows in the direction when you want there to be a flow. By replacing diodes with SCRs, we can control the average amount of voltage across the motor. Procedure. Step 1. Prepare a PCB for the given dimensions. Check the sizes of the components with the soldering position on the PCB. If necessary, slightly alter the dimensions of the PCB track. Step 2. Check the PCB tracks and clean PCB. Step 3. Test the components to confirm its working conditions. SCR. From the datasheets, identify the anode, cathode and gate terminals. Set the multimeter in resistance mode and place the positive lead of the multimeter on the anode of the SCR and negative lead of the multimeter on the cathode lead. The SCR must exhibit infinite resistance under these circumstances and there won't be a continuous buzzer. According to this test, the SCR is fine if its resistance is high. If the SCR displays continuity, it is short-circuited and faulty. Connect the positive lead of the multimeter to the anode terminal and the negative lead of the multimeter to the cathode of the SCR. Now join the anode to the gate with a wire. There should be no resistance between the anode and the cathode. Zero resistance indicates that the SCR is operating in conducting mode. SCR is OK. Step 4. Wire the speed controller circuit on the PCB referring to the circuit schematic and the PCB layout diagram. Get the wired circuit. Step 5. Make connections for the pot, switch, 5 ampere flush type socket, mains 3-core cable, mains 3-pin top with wired circuit on the PCB by using suitable wires. The wired connection are made is to test the wired speed controller circuit before assembling them in the gang box. Therefore, keep sufficient wire lengths in all connections made for the purpose of safety and ease of testing. Step 6. Test the working of the wired circuit by connecting a test lamp load at the output of the speed controller circuit. Check the lamp glow, bringing the two extreme positions of the speed. If the lamp brightness is not varying, vary the position in the wired circuit or connections. Step 7. Test the speed controller using table fan as load and record your observation. Step 8. Assemble the PCB and other associated items so that the wired speed controller is ready for use. Step 9. Now make connections for the pot, switch, 5A flush type socket, mains 3-core cable, mains 3-pin top with the wired circuit on the PCB by using suitable wires, and test the working of wired circuit by connecting a test table fan at the output of the speed controller circuit. Check the table fan, bringing the two extreme positions of the speed. Step 10. Test the universal motor speed controller unit for its range of speed control by connecting an electric drill gun as load and measuring the speed of the gun at minimum, middle and maximum positions of the speed control pot. Step 11. Use contact type tachometer to measure the speed of electric drill gun at different speed control positions of the pot. The wired and tested universal motor speed controller can be effectively used for any practical applications. So preserve the project work made and use it whenever required. In this video, so far we have discussed wiring a universal motor speed controller circuit on the PCB and testing it. Assemble the wired PCB along with the potentiometer and socket in a gang box and test. Test the speed controller with a lamp, fan and electric drilling machine. Check possible minimum and maximum speed adjustments using a contact type tachometer. I hope after watching this video, you can construct and test a universal motor speed controller using SCR. Thank you and have a good day. Hi everyone, in today's video, we are going to discuss how to identify the components and their functions installed in the solar power plant. Objectives: at the end of this video, you will be able to number 1. Visit and interpret the details of the solar power plant. Number 2. Trace and identify the components used in solar plants and write down their functions. Number 3. Prepare and draw the schematic diagram of the solar power plant. Note: trainees may visit the nearest solar power plant to visit the various equipments of the power station and learn the functions of each equipment from the plant engineer. Before entering the power station, the trainees should be aware of the safety rules and regulations prescribed for the plant areas, like wearing personal protective equipment, not touching any power lines or solar panels, etc. First, let us discuss solar energy. One of the main renewable energy sources is the sun. Sunlight and heat are captured and transformed into several types of energy. Solar energy is a technique that converts sunlight into electrical energy either through photovoltaic cells called solar panels. What is meant by photovoltaic cell? A photovoltaic cell, commonly called a solar cell, is a non-mechanical device that converts sunlight directly into electricity. Silicon is the most common semiconductor material used in solar cells, representing approximately 95% of the modules sold today. A semiconductor substance is used in a photovoltaic cell to capture photons released by the sun and convert them into an electron flow. Elementary particles known as photons travel at a speed of 3 lakh km per second when carrying solar radiation. When the photons strike a semiconductor material on the p-n junction, the junction breaks down and electrons start to come out and then to the load. The amount of power generated from the solar panel depends on the amount of sunlight that falls on the solar cell. Step 1. Visit the solar plant and note the details of the plant. Number 1. Capacity of the plant 648 megawatts. Number 2. Output voltage 400 kilovolt. Number 3. Permitted maximum load circuit 1500 amperes. Step 2. Trace and locate the components used in that solar plant. Total solar panel area 2500 acres. Method of mounting panels. The best solar panel performance occurs under direct sunshine exposure. Modules are positioned at an angle facing the south for that to happen. Ground-mounted solar power plants function similarly to rooftop solar systems. This includes absorbing the sunlight to generate an electric charge and then transferring it to the inverter through conductive wires. In ground-mounted panels, the structure is carefully selected with a tilt angle and orientation to maximize sunlight exposure. Controller circuits. The silicon and the conductor in the panel convert the sunlight into DC, which flows into the inverter. The inverter then converts DC to AC since the power requirements are in AC. A module cannot be connected directly to a battery, so a charge controller and an on-charge regulator is used in between module, battery and inverter are required to operate AC appliances. So, the whole system except the module is known as the balance of the system. MPPT controller is one of the main components. As the maximum power operating point is drifting depends on climate, which is unpredictable in short time scale, this controller keeps the solar panels working in the highest energy efficiency ratio. Battery system installed. A battery used in a solar system to store the excess electricity generated by solar panels. Solar panels can be connected directly to the load, but the solar may not be constant, high during the day and low at night. So the high power generated during the day is stored in batteries and may be used during the night. You can then use that stored energy at times when your solar panels don't generate enough electricity, including nights, cloudy days, and during power outages. Solar panel companies prefer lithium-ion batteries because they can store more energy, hold that energy longer than other batteries, and have a higher depth of discharge. DC/AC inverter capacity. Solar panels generate DC, whereas households and industries primarily consume AC. Thus, inverters convert solar energy into a form that is usable by customers. There are two main types of inverters: string inverters and micro inverters. In a large-scale utility plant or mid-scale community solar project, every solar panel might be attached to a single central inverter. String inverters connect a set of panels, a string, to one inverter. That inverter converts the power produced by the entire string to AC. Although cost-effective, this setup results in reduced power production on the string if any individual panel experiences issues such as shading. Microinverters are smaller inverters placed on every panel. With a microinverter, shading or damage to one panel will not affect the power that can be drawn from others, but microinverters can be more expensive. Distribution panel to grid connections. The grid power is in the form of AC, and if we need to supply power to the grid, we need the output of solar plants to be similar to the power of the grid. In this system, the most important condition is that the output frequency and voltage must be matched with the grid's frequency and voltage, and also the power quality maintains the grid standard. Step 3. Note down the daily average power output of the plant for distribution. Step 4. Note specification of solar panels, make voltage ratings, etc. Wattage of each solar panel 100 watts. Output voltage 12 volt DC. Maximum output current 9 amperes DC. Maximum operating temperature 180 degrees Fahrenheit. Type polycrystalline. Make. Step 5. Note tracking system method provided for maximum output. Step 6. Note protection of cells from natural calamities. Step 7. Note installed cells whether in ground level or elevated. Step 8. Draw the schematic diagram of solar power plant as per the guidance. So far, we have discussed how to trace and identify the equipment used in solar plants and their functions, as well as how to prepare and draw the schematic diagram of the solar power plant. Thank you and have a great day. Hi everyone, in today's video we are going to discuss the layout plan and different elements of a wind power plant and their functions. Objectives. At the end of this video, you will be able to number 1. Visit and identify the various components used in wind power generation plants. Number 2. Prepare and draw the schematic diagram of a wind power plant. Let us discuss on wind power plant. A wind power plant, also known as a wind farm, is a facility that harnesses the energy from the wind to generate electricity. Here are the basics of how a wind power plant works. Wind turbines. The wind power plant consists of multiple wind turbines, which are tall structures with large blades. These turbines are strategically placed in locations where there is a consistent and strong wind flow. Wind capture. When the wind blows, it causes the turbine blades to rotate. The shape and design of the blades help capture the kinetic energy of the wind. Mechanical energy. As the blades spin, they turn a shaft connected to a generator inside the turbine. The mechanical energy from the rotation is converted into electrical energy through the generator. Step 1. Visit the windmill power plant and note the details of the plant. Number 1. Capacity of the plant 4.2 megawatts. Number 2. Output voltage 33 kilovolt. Number 3. Maximum load current 200 amperes. Step 2. Trace and identify the equipments or parts used in this windmill power plant. Number of blades 3. Most turbines have 3 blades. When wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both lift and drag. Gearbox. In a wind turbine, the gearbox is an essential component that helps convert the rotational speed of the turbine blades into a speed suitable for generating electricity. The low-speed shaft is connected to a gearbox, which is a set of gears with different sizes. The gears in the gearbox are arranged in such a way that they can change the speed and torque of the rotation. Generator. It's important to note that wind power plants may use different types of generators depending on their capacity and design. Commonly used generators in wind power plants include asynchronous or synchronous generators, with the latter being more prevalent in modern wind turbine technology. The main shaft of the wind turbine is connected to a generator. Exciter. The exciter current is controlled by a turbine controller which senses the wind speed. Based on that, it calculates the power what we can achieve at a particular wind speed. Turbine controller. The wind turbine generator produces alternating current AC electricity as the rotor rotates within the stator windings. The AC output from the generator may have varying voltage and frequency depending on wind conditions and turbine speed. The conditioned DC power is fed into an inverter or other power conversion equipment which converts the DC power back to AC power with the desired voltage, frequency and phase characteristics. The AC power is then synchronized with the grid and transmitted for distribution to consumers. Line Converter Unit. The LCU also includes a grid-side converter (GSC) connected to the stator windings. The GSC converts the AC power from the stator windings to DC power and then inverts it back to AC power with the appropriate voltage, frequency and phase required by the grid. High voltage transformer. The primary winding of the transformer is designed to receive the low voltage AC power and through electromagnetic induction, it converts or step up the voltage to a higher level. Internet Supply Unit (ISU) and Chopper. The output voltage of electrical generator is given to a rectifier, and rectifier output is given to line converter unit to stabilize the output AC that is fed to the grid by a high voltage transformer. An extra unit is based to give the power to internal auxiliaries of wind turbine like motor, battery, etc. This is called internal supply unit. ISU can take the power from the grid as well as from wind. Chopper is used to dissipate extra energy from the rectifier unit RU for safety purpose. Wind turbine. Wind turbines will generally operate between 7 miles per hour, 11 km per hour and 56 miles per hour, 90 km per hour. The efficiency is usually maximized at about 18 miles per hour, 29 km per hour, and they will reach their maximum output at 27 miles per hour, 43 km per hour. A wind turbine turns wind energy into electricity using the aerodynamic force from the rotor blades, which work like an aeroplane wing or helicopter rotor blade. Grid. To connect to the national grid, the electrical energy is then passed through a transformer on the site that increases the voltage to that used by the national electricity system. Tower. Made from tubular steel, the tower supports the structure of the turbine. Because wind speed increases with height, taller towers enable turbines to capture more energy and generate more electricity. The turbines comprise an 80-meter tall tower and 355-meter long blades. Nacelle. The nacelle sits atop the tower and contains the gearbox, low and high-speed shafts, generator and brake. Some nacelles are larger than a house, and for a 1.5 megawatts gear turbine can weigh more than 4.5 tons. Hub. Part of the turbine's drivetrain. Turbine blades fit into the hub that is connected to the turbine's main shaft. Low-speed shaft. Part of the turbine's drivetrain. The low-speed shaft is connected to the rotor and spins between 8 to 20 rotations per minute. Brake system. A turbine brake keeps the rotor from turning after it's been shut down. Once the turbine blades are stopped by the controller, the brake keeps the blades from moving, which is necessary for maintenance. Step 3. Note down the daily average power output of the plant. Step 4. Note down the minimum RPM of turbine to maintain the rated voltage. Step 5. Note down the chopper, circuit characteristics and its importance in the turbine controller. Step 6. Note down the protection provided from natural calamities. So far, we have discussed identifying the various components used in wind power generation plants and preparing and drawing the schematic diagram of a wind power plant. Hi everyone, in today's video, let us discuss how to assemble and connect a solar panel for illumination. Objectives. At the end of this video, you will be able to number 1. Calculate the total number of cells required to make a series parallel combination for one panel. Number 2. Fix the 4 LED lamps 12 volt by 3 watt at the required position in the lamp. Number 3. Wire the circuit from the panel to the light in the lamp. Number 4. Fix the panel board with control and protection devices to illuminate the lamp. Number 5. Assemble and install solar panels at mid-clamp and rooftop. Let us arrange the tools, equipments and materials required for this exercise. Number 1. Trainee's toolkit, 1 number. Number 2. Power drilling or hammering machine with suitable drill bits, 1 set. Number 3. Solar panel, 15 watt, 12 volt, 1 number. Number 4. Solar cells, 0.45 volt, 125 megawatt per centimeter square, 540 cells. Number 5. Connecting wires 1 square millimeter PVC cable as required. Number 6. Gang box with 1 switch, 250 volt by 5 amperes, 1 number. Number 7. Panel frame suitable to fix the wired solar cells, 4 number. Number 8. LED lamp with shaded reflector, 12 volt by 3 watt, 4 numbers. Procedure. Task 1. Calculate the number of cells required to illuminate one panel. Assume the lamp voltage is 12 volt and power 3 watts. Number 1. Determine the number of solar cells in series group. Number of cells in series group is equal to total required voltage by volt or cell. One cell is equal to 0.45 volt and 57 milliamperes is equal to 12 volt by 0.45 is equal to 27 cells. 27 into 0.45 is equal to 12.15 volt. Considering line losses voltage of 0.15 volt taken as extra, 0.15 volt taken for line lines. Number of series group required for the correct of 250 milliamperes is equal to current required for one lamp upon current in one series group. LED lamp requires 250 milliamperes is equal to 250 milliamperes upon 57 milliamperes is equals to 4.38 is equals to 5 groups. Task 2. Assemble of solar panel and its installation. Step 1. Collect solar cells and make the series connection. 27 cells in series on the panel board. Step 2. Prepare 5 number of series connection and wire them for parallel. Step 3. Make 4 similar solar panels in total. Step 4. Locate the suitable places and fix it on rooftop where sunlight are falling directly. Locate the places of fixing panels should not be under shadows of trees and buildings, etc. Task 3. Fix lamps and gang box. Step 1. Locate the lamp position and switch position as short as possible from solar panel for all the 4 panels. Step 2. Wire the panel to gang box and the lamp neatly. Wiring can be done in PVC conduit or PVC casing and capping to give aesthetic look. Step 3. Fix the lamp assembly and complete the wiring with switch control. Step 4. Test the wiring for any short or open circuit fault. Step 5. Connect the wire to the panel terminals and measure the voltage at lamp terminal. Step 6. Connect the lamp and operate the switch for illumination. Step 7. Report to your instructor for his approval. Task 4. Assemble and install solar panel at mid-clamp rooftop. Step 1. Select the roof without shading for the solar panel installation. Step 2. Check that sure the direction of installation of the solar panels receives more sun rays to mount the solar panel. Select an area of roof to install the solar panels that gets the sunlight rays as long as possible all days. The solar panels can either be mounted flush on the roof or stand or mounted at an angle to maximize the position of accessibility to the sun's direct rays. Step 3. Collect contact pipe with M8 into 25 contact base pipe. Step 4. Fix the contact support pipe and contact pipe with M8 into 25 screw. Step 5. Take 2 fixed title rack and position them with rail. Step 6. Put one panel on the rack. Use 2 end clamps to hold and fix it. Attention, end of rail distance is must. Step 7. Install the modules and mid clamp and end clamp. Step 8. Install panel by fixing mid clamp between panels. Step 9. Select the best perfect angle for solar panels with the help of manual to produce the maximum power. Step 10. Drill the hole on the roof with the help of drilling machine. Step 11. Fix the frame with the help of screws and place the panel on frame. So far, we have discussed how to calculate the total number of cells required to make a series parallel combination, fix and wire the 4 LEDs required in the lamp, and install solar panels at the mid-clamp and rooftop. Thank you. Have a good day.
A warm welcome to this session of Electrician Trade. Today, we are going to practice installation of insulators used in HT-LT lines for a given voltage range. At the end of this session, you will be able to identify the type of HT-LT line insulators, install the shackle type insulator on HT overhead line, install the pin type insulator on LT overhead line. Electrician toolkit and equipments required. Insulated combination plier 200 mm, DE double-ended spanner set 6 mm to 25 mm, adjustable spanner 6 mm to 25 mm, safety belt, wooden or nylon mallet half kg, ladder 6 meters long, jute rope 25 mm diameter and 15 meters length, wire stripper 25 mm, megger 500 volts, C-clamp, wire stretcher 25 mm, shackle insulator, porcelain 1 kilovolts, pin insulator, porcelain 1 kilovolts, suspension insulator, strain insulator, ring insulator, stay or egg insulator, cotton waste, binding wire 14 SWG aluminium, scrap piece of ACSR conductor of length 1 meter for bow, sandpaper or emery sheet, flat aluminium tape, protective grease suitable to apply over the ACSR line conductor, line accessories. Before getting into the practice, let us know some basic information on HT, LT lines and insulators used in HT, LT lines. What are HT, LT lines? HT means high tension or high voltage supply. It carries the bulk power such as 11 kV, 33 kV, 66 kV and 110 kV. It is used to transmit power at large distances by increasing voltage and decreasing current. LT means low tension or low voltage supply. It has high current carrying capacity and the voltages in general. It is used to distribute power in local areas and in small distances. Line insulator. Line insulator in an overhead line is to hold the live conductor to prevent leakage of current from the conductor to the pole. They are made of porcelain clay and they are thoroughly glazed to avoid the absorption from the atmosphere. Glass T-tight and special combination materials are also used for line insulators in an overhead line to a limited extent. Properties of line insulator: high mechanical strength to withstand conductor load, wind load, etc. High electrical resistance of insulator material to avoid leakage currents to the earth. High relative permittivity for high dielectric strength. Pure non-porous insulator material for high permittivity. High ratio of puncture strength to flash over, to withstand flash over voltages. Common types of line insulators: pin insulator, shackle insulator, suspension insulator, strain insulator, post insulator, stay insulator and disc insulator. Pin insulator. Pin insulators are used for holding the line conductors on straight running of poles. It is secured to the cross arm on the pole. The conductor passes through the groove on the top of it and is bound by annealed wire of the same material as the conductor. These are used in LT lines. Pin insulators are further classified into three types: single shed pin insulator, double shed pin insulator, triple shed pin insulator. Shackle insulator. Shackle insulators are generally used for terminating on corner poles, on sharp curves, and for service connections, medium voltage lines only. These insulators are used in horizontal position or vertical position. These insulators are used for below 3 kV. These are used in LT lines. Suspension insulator. Suspension type insulators are used with steel towers for HT lines for partial protection from lightning. They consist of number of porcelain discs connected in series by metal links in the form of a string. Each disc is designed for low voltage of 11 kV. The suspension provides greater flexibility to the line. Post insulator. Post insulators are used for mounting of buses, dropout fuses, line conductors, gang-operated air brake switches. These are of outdoor type and are available in 11, 22 and 33 kV ranges. They are used in LT lines. Stay insulator. Stay insulators are also known as strain insulators and are generally used up to 33 kV line. Strain insulators are used to relieve the tension in the line when there is a dead end or corner or sharp curve. These insulators should not be fixed below 3 meters from the ground level and prevents the bending of the pole due to tension of the conductor. They are used in LT lines. Disc insulator. Disc insulators are made of glazed porcelain or tough glass and are used as insulators at dead ends or on straight lines as suspension type for voltages 33 kV and above. They are used in LT lines. Identifying the type of HT-LT line insulators for given voltage ranges. First of all, we need to identify the type of HT-LT line insulators to be used for a given voltage range. By knowing the voltage ranges and the purpose of insulators, we can choose the correct insulator for the correct place. For example, we need to choose an insulator for LT line and for holding conductors on straight running poles. For these, pin type insulators can be used. Pin insulator. Holding line conductors straight running poles. Shackle insulator. Terminating on corner poles. Suspension insulator. Providing suspension arrangement to the line. Strain or stay insulator. To avoid greater tension at corner or sharp curves at dead end of the line. Post insulator. Mounting of buses, dropout fuses, line conductors and switches. Disc insulator. At dead ends or on straight lines. Installation of shackle type insulator on HT overhead line. Fasten the safety belt, lay the ladder on the pole. Release the conductor from the reel, measure the actual span plus sag and binding line. Keep 2 lengths of the conductor. Check the shackle insulator for its damage and select a good one. Check the assembly of the shackle insulator for its proper fitting. While working on the ladder should be held by the helper to avoid slipping. Climb up the ladder with the guide rope and tool kit. Position yourself conveniently on the cross arm. Tie the safety belt end to the cross arm. Send one end of the guide rope to the helper and ask him to tie to the shackle assembly and lift it to the top. Fix the shackle insulator to the cross arm by C-clamps. Get the draw pulley from the ground and secure it on the cross arm. Interlace the rope through the pulley and send the other end to the helper. Ask the helper to properly tie the overhead conductor to the rope and lift the conductor to the cross arm position. Twist the end portion of the conductor over the main line conductor. Bind the shackle insulators with the one fixed at the last cross arm. Note: ground clearance of the overhead conductor should not be less than approximately 5 meters for low and medium voltages. Get down from the pole after checking the binding. Install the pin type insulator on LT overhead line. Climb the next pole following the previous safety procedure. Lift the conductor and keep it on the pin insulator. Ask the other helper to lift and stretch the conductor with wire stretcher. Fix the pin insulator to the cross arm of the existing pole in the correct position. Bind the pin insulators by annealed wire of the same material as the conductor as per the procedure. Bind the free ends of the binding conductor over the line conductor tightly in the opposite direction. Complete the binding by giving about 15 turns on both sides. Binding should be tight enough without any gap. Cut the extra binding wire and round off the raised ends. Repeat the procedure for the other pin insulator by the side of the same cross arm. After finishing the installation of insulators on poles, we need to ensure the insulations between the conductors and between the conductors and earth. For this testing, a megger of 500 volt is used to measure the insulation between conductors and insulation resistance between conductors and earth. Place the probes of the megger between the conductors and between conductors and earth points as shown here, and measure the values. Record the values in the table. Recap. In this session, we have learnt how to identify the type of HT, LT line insulators. Install the shackle type insulator on HT overhead line. Install the pin type insulator on LT overhead line. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session of Electrician Trade. Today, we are going to see drawing single line diagram of transmission and distribution system. At the end of this session, you will be able to trace the transmission and distribution system which you have visited. Identify the equipments in sequential stages of transmission and distribution system. Prepare the layout and draw the single line diagram of the transmission and distribution system. Electrician toolkit and equipments required. Hand notes on visited power plant, transmission and distribution system. Drawing sheet, pencil, eraser, scale, personal safety protections. Transmission and distribution system. Before getting into practice, let us have a brief view of AC power supply system. The conveyance of electric power from a power generating station to the consumers is called electrical supply system. The electrical power supply system consists of three main components. They are the power station or generating station, the transmission system and the distribution system. Generating station. The place where electric power produced by the parallel connected three-phase alternators or AC generators is called generating station. Single line diagram of transmission system. Transmission system. The transmission system can be categorized as primary transmission and secondary transmission. High voltage primary transmission. The electric supply, that is 66 kV, 132 kV, 220 kV or greater is transmitted to the load center by 3-phase, 3-wire overhead transmission system. High voltage secondary transmission. The area far from the city which are connected with receiving station by line is called secondary transmission. Line diagram of distribution system. Distribution system can be categorized as primary distribution and secondary distribution. Primary distribution. At a substation, the level of secondary transmission voltage, that is 66 kV or 132 kV, is reduced to 11 kV by step-down transformers. 3-phase, 3-wire systems are used in primary distribution. Secondary distribution. From the primary distribution line, that is 11 kV or 415 volts, electric power is given to the secondary distribution substation. This substation is located nearby consumers area where the level of voltage is reduced by step-down transformers is 450 volts or 240 volts. These transformers are called as secondary distribution transformers. This 415 volts or 240 volts line is called the secondary distribution line. In this line, 3-phase, 4-wire systems are used. Layout of distribution system. Secondary distribution system can be divided into 3 parts. Feeders. Those electrical lines which connect substations to distributors are called feeders. Distributors. Those tappings which extract LT power supply from feeder lines to the consumers are called distributors. Service mains. The normal cable which is connected between distributors and consumers load terminal are called service mains. Equipments in sequential stages of transmission system. I hope now you all have understood the basics of AC electric power supply system. Now let us start our practice on drawing single line diagram of transmission and distribution system. For this exercise, we need to visit the nearby transmission and distribution line system and power plant. We have to identify the sequential stages of transmission and distribution line system over there. Trace and identify the various types of equipments like transformers, feeders, circuit breakers, isolators, CT and PT, etc. from the generation to the consumer points in the sequence of transmission and distribution system and note them carefully. Note down their details in Table 1 for the transmission system and Table 2 for the distribution system. Power transformer. Capacity 11 kV or 220 or 500 kV. Set up the generation voltage. Circuit breaker. Handling capacity 66 to 500 kilovolts. Isolate equipment for maintenance and changing the transformers. Bus bar. Metal conductors of copper. These are usually rectangle, tubular, bare copper bars supported with insulators. Steel tower. These are various shaped iron made of angles. Height of 23 to 30 meters. To set up HT and EHT lines. Primary grid. Handles capacity of 220 or 66 kilovolts and more. Used at primary transmission lines. Feeder. Conductor wires. Electric lines which are connected to generation station to substation. Power distribution centers. Isolator. Depends upon the capacity of the substation. It is a type of switch which is employed only for isolating the circuit when the current has only been interrupted. PT or potential transformer. Depends upon circuitry. It is an instrument transformer which is used to measure high AC voltages by means of its proportionate lower values. CT or current transformer depends upon current capacity. It is an instrument transformer which is used to measure high AC current by means of its proportionate lower values in its secondary side. Tab change equipment provided HV side, used to regulate the output voltage manually according to the line voltages. Control panel room depends upon the capacity of the substation. It consists of MCCB's control equipments, meters, or assembled or mounted in steel panels in the control room. Distribution transformer 33 kilovolts or 11 kilovolts to 415 or 250 volts, which steps down the primary voltage of 33 kilovolts or 11 kilovolts to secondary distribution voltage of 415 or 250 volts. Circuit breaker depends upon the capacity of the substation, which automatically cuts off power supply when senses the fault in the system. Lightning arresters power 18 into 10 power 5 kilowatt. It is a protective device to protect valuable equipments. It arrests and charges over voltage to earth during lightning strokes. Air breaker switches or isolators depends upon the capacity of the substation. It is used to isolate equipment for maintenance or replacement, and that can be operated manually. Insulators depends upon voltage range. To insulate line conductors or equipment at different voltages with respect to the ground stretcher. Capacitor bank depending upon capacity of substation. To improve power factor. Earthing in general 0 to 6 ohms. It is very important for safety of operating personnel as well as electrical devices. Fencing more than 1.8 meter provided at outdoor substation. Compound restriction entry of unauthorized persons and live animals. Distribution panel. It is a metallic cabin. It consists of MCCBs, control equipments, meter, and relays are housed in the control room. CTs or current transformer depends upon current capacity. It is a device which is used to measure high current by the transformation of current from a higher value to lower value. PTs or potential transformer depends upon circuitry. It is an instrument transformer which is used to measure high AC voltages by means of its proportionate lower values. Feeder, conductor wires, electric lines which are connected to generation station to substation. Power distribution centers. Distributor depends upon consumer capacity. Distributor lines are low voltage lines from where the tapping of power supply lines are taken for residential and commercial use. Service mains. Cable length depends upon distance between distributors and consumer. Now, cable capacity depends upon power rating. The normal cable which is connected between distributors and consumer load terminal are called service lines or service mains. Note down the earthing system. Note the different values of earth resistance displayed in earth pit. Note down which equipment and installation requires least earth resistance value and irregular value. With the help of above equipment lists and the notes taken in our visit to power plant, transmission and distribution line system, locate the places of equipments in sequence and draw the single line diagram of transmission and distribution system which you have visited. The typical single line diagram of AC power supply system may look like this figure, and the typical single line diagram of the distribution system may look like the diagram shown here. Recap.
In this session, we have learned to trace the transmission and distribution system
of which you have visited. Identify the equipments in sequential stages of transmission and distribution system. Prepare the layout and draw the single line diagram of the transmission and distribution system. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session of Electrician Trade. Today, we are going to see measurement of current carrying capacity of a conductor for given power supply. At the end of this session, you will be able to identify and select three different conductors, that is copper, aluminium and alloy. Connect the circuit and measure the breaking current of the conductor. Electrician toolkit and equipments required. Electrician toolkit DC ammeter 0 to 10 amperes, DC voltmeter 0 to 15 volts, lead acid battery 12 volts 60 ampere hour, rheostat, wooden board with switch 16 amperes 250 volts, 32 SWG copper conductor 10 cm, 32 SWG aluminium conductor 10 cm, 32 SWG alloy conductor 10 cm, 2.5 square millimeter connecting copper wires, standard wire gauge. Conductors. Before getting into our exercise, let us have a brief view on conductor materials. Conductors are those substances through which electricity can flow. There are different types of conductor materials available. Let us see some of them. Copper conductors. Copper has high conductivity, greater tensile strength, high current density. It has more current carrying capacity per unit cross-sectional area. Copper was a preferred material for overhead conductors, but due to its higher cost, it is rarely used. Copper conductors are available in both bare conductor and insulated copper conductors. Aluminium conductors. Aluminium conductor has about 60% of conductivity of copper conductor and has almost half the weight of the copper conductor. Since it has an edge over copper, they are being widely used for overhead conductors. Alloy conductors. There are many other metals and combination of one or more metals called as alloys are available that conduct electricity. Copper cadmium alloys are high cost conductors. At extreme conditions, high strength alloys such as phosphor bronze are also used. Every conductor material has its own property. One of the properties of the conductor is the current carrying capacity of the conductor. The current carrying capacity of the conductors. The current carrying capacity of the conductors is the maximum value of the current that the conductor can be carried continuously without exceeding its specified temperature rating. So, it is necessary to know the current carrying capacity of the conductor. Connect the circuit and measure the breaking current of the conductor. Now, let us start our exercise. We are now going to measure the current carrying capacity of the conductor for a given power supply. Check the tools, materials and instruments for their good condition. Now, for our exercise, let us select copper conductor, aluminium conductor and alloy conductor of 32 SWG of 10 cm in length each. Ensure all the conductor should have same SWG and length. First, connect the copper conductor on the test board as shown. Connect rheostat, ammeter, voltmeter and battery as shown. Keep rheostat at cold end, that is, in its maximum resistance position and switch on the circuit. Note the ammeter and voltmeter readings. Now move the rheostat to its middle position and note down the ammeter and voltmeter readings. Adjust furthermore the rheostat position to the hot end, that is towards its minimum resistance position slowly while keeping a watch on the conductor. It may break now. If the conductor is not broken, then increase further the position of rheostat towards the hot end slowly till the conductor breaks and note down the corresponding meter readings. Note down the current value, and this is the maximum current carrying capacity of the given copper conductor. Connect the aluminium and alloy conductor one by one and repeat the steps to find the maximum current capacity of the corresponding conductors and note them down in the table. Test results. From the tabulation value, we can conclude the current carrying capacity of a given conductor material. Maximum current capacity of copper conductor is 2.18 amperes. Maximum current capacity of aluminium conductor is 1.30 amperes. Maximum current capacity of alloy conductor is 0.87 amperes. Recap.
In this session, we have learned how to identify and select three different conductors, that is copper, aluminium and alloy. Connect the circuit and measure the breaking current of the conductor. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you.
Jai Hind. Today I am here to discuss about the importance of tender presentation. Tender presentation is a critical state of tender formulation and tender procedures. It is usually done